The cosmos is almost entirely unknown to us. We map the glittering stars and majestic spirals, but these are just the visible crumbs on a vast, dark table. Lurking in the shadows are structures so strange they defy our textbooks: dark galaxies. These are cosmic ghosts, immense collections of matter where light barely flickers, dominated by the invisible grip of dark matter. They are the universe's best-kept secrets, and their existence challenges everything we think we know about how galaxies are born and how they die. By the end of this exploration, you will know the 25 specific dark galaxies that make even seasoned astronomers uneasy. What if the shining galaxies we cherish are rare exceptions in a sea of darkness? How many of these phantoms are silently orbiting our own Milky Way? The answers reshape reality. What does it mean if the true universe is one we cannot even see? Our first dark galaxy is a cosmic paradox, a ghost of staggering proportions named Dragonfly 44. It drifts within the Coma Cluster, a dense metropolis of galaxies over 300 million light-years away. At first glance through a telescope, Dragonfly 44 is barely there. It is what astronomers call an ultra-diffuse galaxy, a wispy, faint smudge of light so dim you could look right through it to the galaxies behind. Its handful of stars are spread so thin that the galaxy appears almost transparent, like the delicate wings of its insect namesake. But this ethereal appearance is a profound deception. Measurements of how its few stars move reveal a terrifying truth. They are whirling around at velocities that should tear the entire structure apart. The only thing holding this fragile wisp together is the immense, invisible gravitational anchor of dark matter. The math is staggering. For Dragonfly 44 to exist, over 99.99% of its mass must be made of this mysterious substance. In practical terms, this galaxy has the width of our Milky Way, but only 1% of its stars. It is a titanic halo of shadow with a few lonely fireflies trapped inside. This discovery shattered expectations. Standard models of galaxy formation say that a halo of dark matter this massive should have attracted and compressed vast amounts of gas, triggering a frenzy of star birth, resulting in a brilliant spiral galaxy like our own. Dragonfly 44 did the opposite. It gathered its dark matter and then, for reasons we do not understand, it failed. It is a cosmic stillbirth, a monument to a process that started and then simply stopped. This makes it a prime candidate for what theorists call a failed galaxy, a dark matter structure that never truly ignited. Its very existence whispers a disturbing question. How many other such phantoms, massive yet dark, are floating silently in the voids between the stars we see? The profound silence of Dragonfly 44 is mirrored much closer to home, hidden in our own galactic backyard. Drifting through the halo of the Milky Way is a ghost of such subtlety that it evaded detection for decades, a dwarf galaxy named Antlia II. Discovered only in 2018 by the European Space Agency's Gaia spacecraft, this object redefined what we thought a galaxy could be. Antlia II is incredibly faint, 10,000 times dimmer than the faintest galaxy you could ever hope to see with the naked eye. Its stars are so widely dispersed that if our Sun were among them, the nearest stellar neighbor would be several light-years away, plunging its planetary systems into near-total darkness. Yet, for its pathetic glow, Antlia II is absurdly large. It spans nearly one-third the diameter of our entire Milky Way galaxy. This combination is bizarre, a cosmic puff of smoke as wide as a continent. The mystery deepens when we consider its survival. A structure this wispy, orbiting a giant like the Milky Way, should have been shredded to pieces long ago by our galaxy's immense tidal forces. It should be a stellar stream, not a coherent galaxy. The fact that it still holds together, however loosely, points to one inescapable conclusion. Antlia II must be embedded within an enormous, cushioning halo of dark matter. This invisible scaffold provides the gravitational integrity that its visible stars alone cannot. But here lies the puzzle. According to our leading models, a dark matter halo massive enough to protect Antlia II should have also attracted far more gas and spawned many more stars. It should be brighter, so why is it so dark? Astronomers are now wrestling with this contradiction. Perhaps its dark matter is distributed in an unusual, fluffy profile that stifled star formation. Or maybe it endured a violent history of stellar explosions that blew away its star-making gas long ago. Antlia II is a fragile phantom surviving against all odds, and its continued existence is a direct challenge to our theories about how dark matter halos behave. It forces us to ask, if this one slipped by us for so long, how many other faint, massive shadows are orbiting us right now, completely unseen? The eerie silence of these dark matter giants leads us to a discovery that seemed to break all the rules entirely. In the constellation Cetus, a galaxy named NGC 1052 DF2 presented astronomers with the opposite and arguably more terrifying puzzle. When first measured, this faint, blob-like galaxy appeared to contain almost no dark matter at all. Its stars were moving at a sedate, leisurely pace, their speed perfectly explained by the gravitational pull of the visible stars and gas alone. There was no extra tug, no hidden mass, no signature of the invisible scaffold that supposedly holds every galaxy together. This finding sent shockwaves through cosmology. If confirmed, it meant dark matter was not an inseparable part of a galaxy, but something that could be stripped away or never acquired in the first place. It threatened the very foundation of our standard model of the universe, where dark matter is the essential skeleton upon which all luminous structure is built. The idea of a galaxy without it was not just surprising, it was existentially frightening. It implied our understanding of cosmic ingredients was fundamentally flawed. The controversy erupted almost immediately. Other teams re-examined the data, focusing on the galaxy's distance. This is a critical number because if you get the distance wrong, you miscalculate both the galaxy's true brightness and the speed of its stars. Some studies argued that NGC 1052 DF2 was actually much closer than the original team claimed. If that were true, the galaxy would be intrinsically smaller and dimmer, and its stars would be moving slower, meaning their motion could once again require dark matter to explain. The debate became a technical tug-of-war over measurements of cosmic scale. This fierce controversy highlights a deeper, more unsettling truth. The fact that a single galaxy's properties can be so hotly contested shows just how fragile our grasp on the dark universe really is. We are probing the limits of our instruments, interpreting faint signals across unimaginable voids. Whether NGC 1052 DF2 is truly empty of dark matter or not, its legacy is profound. It forced scientists to confront the uncomfortable possibility that the dark matter recipe might not be universal, that some galaxies could be built differently. This opens a door to a cosmos far more diverse and strange than our tidy models predicted, where the rules of construction are not written in stone but in shadow. The controversy surrounding DF2 was still simmering when its close neighbor, NGC 1052 DF4, was thrust into the spotlight. This galaxy, a near twin in size and appearance to its controversial sibling, seemed to double down on the anomaly. Initial studies of DF4 revealed the same perplexing signature, its stars moving too slowly to require any significant dark matter halo. It was as if astronomers had found not one, but two cosmic rule breakers living in the same neighborhood. The implications were staggering. A single galaxy without dark matter could perhaps be written off as a bizarre fluke, a cosmic accident or a measurement error. But two of them, right next to each other, suggested something far more deliberate. It pointed to a new, unknown process at work, a mechanism that could somehow separate the normal matter of stars and gas from the dark matter that supposedly cradles it. This twin discovery challenged the most fundamental assumption in modern cosmology, that dark matter is the indispensable gravitational glue for all galaxies. If these two structures could exist without it, what did that say about the countless other faint, diffuse galaxies we are only beginning to catalogue? The scientific hunt intensified, focusing on a compelling and violent theory. Perhaps DF2 and DF4 were not born this way, but made this way. They reside near a massive elliptical galaxy called NGC 1052. One leading idea proposes that both dwarf galaxies were once normal, dark matter, rich satellites that strayed too close to their giant neighbor. As they plunged through the dense central regions of NGC 1052, the relentless tidal forces, the gravitational pull of the larger galaxy, could have acted like a cosmic sieve. The dark matter, spread out in a diffuse halo, might have been easily stripped away and scattered into intergalactic space. The stars, however, being more concentrated and tightly bound, could have held together, leaving behind the luminous dark matter, poor ghosts we see today. This scenario of tidal stripping offered a potential escape from the theoretical crisis, but it came with its own stringent requirements. The timing and the geometry had to be just right. Furthermore, if this stripping was so efficient, why do we not see more galaxies like this? The puzzle of the twins forced astronomers to confront an uncomfortable truth. We may not fully understand the marriage between dark matter and the stars it supposedly governs. Their bond might be more fragile, more conditional than our models have assumed. The silent testimony of DF2 and DF4 suggests that in the rough and tumble environment of galaxy clusters, the dark universe can be torn apart, leaving behind luminous orphans that defy our textbooks. But the story of dark matter is not only about its absence. For every ghostly galaxy seemingly devoid of it, there is another where dark matter reigns with absolute terrifying dominance. Enter Segue 1, a name that sounds like a gentle transition but belongs to one of the most extreme objects in the cosmos. This ultra-faint dwarf galaxy is a satellite of our own Milky Way, a tiny, dim speck of light lost in the glow of our galaxy's stellar disk. Its stellar population is minuscule, a mere handful of ancient stars, perhaps only 1,000 in total, clumped together in a volume spanning several hundred light years. If you stood on a planet in Segue 1, the night sky would be almost completely black, punctuated by just a few faint, nearby suns. Yet this pathetic collection of stars tells a lie about its true nature. The motions of those few stars are frantic, whipping around at speeds that reveal a gravitational grip of shocking strength. When astronomers calculate its mass-to-light ratio, a measure of how much total mass there is compared to the light its stars produce, the numbers become almost incomprehensible. For Segue 1, this ratio soars into the thousands. To put that in human terms, it is as if you found a single, flickering candle in a vast warehouse. But when you tried to move it, you discovered the candle weighed as much as a battleship. Over 99.9% of Segue 1's mass is invisible dark matter. It is not just a galaxy with dark matter, it is a dark matter clump that, almost as an afterthought, managed to capture a few stars. This makes it a potential fossil, a pristine relic from the universe's earliest epochs. Theorists believe the first structures to ever form were tiny, dense halos of pure dark matter. Segue 1 could be a direct descendant of those primordial seeds, a surviving fragment of the cosmic dark age that somehow, against all odds, acquired a sprinkling of stars. Scientists study it with a mixture of awe and fear, for it offers a direct window into conditions over 13 billion years ago, but that window is clouded. The fear is that we might misinterpret its signal. Is its incredible darkness due to its ancient, pristine nature, or was it sculpted by violent encounters with the Milky Way that stripped away its gas and suppressed star formation? Getting this answer wrong means misreading the very first chapter of galactic history. Segue 1 is a whisper from the dawn of time, a whisper written almost entirely in the language of shadow. While Segue 1 is a whisper from the cosmic dawn, another nearby phantom screams with a potential signal we have been desperate, yet almost afraid to find. Triangulum II is a dense, compact dwarf galaxy orbiting the Milky Way, a mere speck of ancient starlight. Its handful of stars are old and metal-poor, telling us it formed long ago and has lived a quiet, isolated life. But the quiet ends when we measure how those stars move. Their velocities are chaotic and wildly high, zipping around in a gravitational maelstrom. This high-velocity dispersion points to one thing, a core of dark matter so incredibly dense and massive that it defies easy explanation. For its tiny visible size, Triangulum II possesses one of the highest dark matter densities ever measured. It is a dark matter knot pulled tight and left to simmer in the galactic halo. This extreme concentration makes it a perfect natural laboratory for one of the most profound experiments in modern physics. Scientists have long theorized that dark matter particles, under the right conditions, could annihilate one another. When two of these hypothetical particles collide, they would obliterate each other in a flash of energy, producing a cascade of secondary particles, including gamma rays, the most energetic form of light in the universe. We have built incredibly sensitive detectors deep underground and in space, hoping to catch a glimpse of this process, and here is where the fear sets in. Observations from the Fermi Gamma Ray Space Telescope have revealed a faint but persistent glow of gamma rays emanating from the heart of Triangulum II. This glow is exactly what models predict would come from a dense clump of annihilating dark matter. The implications are staggering. If this signal is real, it would be the first direct, non-gravitational evidence of dark matter's existence. It would crack open the mystery, revealing not just that dark matter is there, but something fundamental about what it is made of. Yet, this potential triumph is laced with profound terror. The same signal that confirms our theories could also unravel them. The intensity of the gamma rays, if truly from annihilation, suggests a dark matter particle that is different, perhaps more powerfully interacting than our most favored models predict. It could force us to scrap decades of theoretical work and start from scratch. There is a more mundane but equally critical fear. Could this gamma ray glow have a simpler astrophysical explanation? Perhaps it comes from a cluster of unseen pulsars, the spinning corpses of dead stars hidden within Triangulum II. Distinguishing between a dark matter breakthrough and a celestial false alarm is a painstaking, nerve-wracking process. So we watch Triangulum II with bated breath. It holds a secret in its dark heart, a signal that could be the key to understanding the universe's hidden architecture or a cosmic mirage that leads us deeper into the dark. The fear is not of the answer, but of misreading the question entirely. The potential for dark matter to reveal itself through annihilation in places like Triangulum II suggests these shadows are not passive, but active participants in cosmic physics. Yet not all dark galaxies are dense knots of potential energy. Some are the opposite, cosmic phantoms so diffuse they seem on the verge of dissolving into the void. One of the most spectacular examples of this ghostly fragility orbits our own galaxy, a satellite named Crater 2. Discovered just in 2016 in data from the VLT Survey telescope, Crater 2 immediately stood out not for its brightness but for its profound subtlety. It is incredibly faint, so dim that its light is drowned out by the ambient glow of the night sky itself, making it impossible to see with traditional telescopes. It was found only by statistically mapping the positions and motions of individual ancient stars that were moving together. What emerged was a ghostly outline, a vast and wispy collection of stars spread across an astonishing distance. Crater 2 is enormous, the fourth largest satellite galaxy of the Milky Way in terms of physical size, stretching over 7,000 light-years across. Yet it emits less than 1% of the light of the much smaller, but far denser Sagittarius dwarf galaxy. This combination of great size and feeble glow gives Crater II an almost fluffy appearance, like a cosmic dandelion seed caught in our galaxy's gravitational breeze. Its surface brightness is so low that if you could somehow place it in the place of our own galactic center, its stars would be so spread out that our night sky would appear almost unchanged, just slightly more populated with very distant, faint points of light. This extreme diffuseness is the core of the mystery. A structure this large and this faint should not be able to hold itself together against the immense tidal forces of the Milky Way. Its stars should have been pulled into a long, thin stream encircling our galaxy long ago. The fact that it remains a coherent, albeit fluffy, sphere tells us it is held together by gravity from something we cannot see. Crater II must be embedded in a massive, extended halo of dark matter. But here is the challenge for theorists. This dark matter halo appears to be unusually spread out or puffy itself. In most models, dark matter halos have a dense central core. Crater II's halo seems to be more evenly distributed, lacking that strong central concentration. This fluffiness challenges our standard models of satellite galaxy evolution. One leading theory suggests that Crater II may have experienced intense bursts of star formation in its distant past. The powerful stellar winds and supernova explosions from that era could have blown out much of its gas and, critically, may have also pushed and smoothed out its dark matter distribution, creating this expansive, diffuse profile. Another, more unsettling idea is that our understanding of dark matter's fundamental properties is incomplete, and that under certain conditions, it naturally forms these fluffy, low-density halos. Crater II is a silent testament to a gentler, more elusive form of darkness. It is not a dense knot of annihilating particles, but a vast, soft, shadowed cloud. A reminder that the invisible scaffolding of the universe may come in shapes and textures we are only beginning to map. The gentle ghost of Crater II has a distant, and perhaps even more ethereal, cousin in the realm of our nearest galactic neighbor. Circling the great Andromeda galaxy, some 2.5 million light-years away, is a phantom so diffuse it stretches the very definition of a galaxy. Its name is Andromeda 19. This dwarf spheroidal galaxy is a study in extremes. Its diameter is staggering, spanning several thousand light-years, a size that rivals far brighter and more famous dwarf galaxies. Yet this vast expanse is populated by so few stars that its light is spread impossibly thin. The surface brightness of Andromeda 19 is among the lowest ever measured. To human eyes, even with the most powerful telescopes, it is not a distinct object but a subtle statistical excess, a barely perceptible smudge against the black velvet of space that can only be mapped by painstakingly counting and tracking its individual ancient stars. It is not merely dim, it is nearly invisible, a galactic apparition. This profound darkness births a specific and growing fear among astronomers. Andromeda 19 is not an oddity, it is a prototype. If something this large and this faint can exist, orbiting a galaxy we have studied for centuries, how many more are hiding in plain sight? Our entire census of the local universe, our map of satellite galaxies around the Milky Way and Andromeda, is built upon what we can see. Our telescopes have a brightness threshold. Anything fainter than that threshold simply disappears into the background glow of the night sky, both the natural sky glow and the scattered light from within our own solar system. This means our galactic family portrait is incomplete. We are only seeing the brightest, most obvious siblings. The shy, ghostly ones like Andromeda 19 are missing from the picture. The implications are deeply unsettling for our understanding of cosmology. Theories of galaxy formation, especially the leading lambda cold dark matter model, make very specific predictions about how many satellite galaxies should orbit a large spiral like the Milky Way or Andromeda. For years, astronomers wrestled with the missing satellites problem, where observed satellite counts fell far short of theoretical predictions. The discovery of ultra-faint dwarfs like Segue 1 and Crater 2 helped close that gap. But now, the fear has inverted. What if the problem is not that satellites are missing, but that our eyes are blind to an entire population? If galaxies as diffuse as Andromeda 19 are common, then the true number of satellites could be vastly larger than our models predict. This would not solve a problem. It would create a new and potentially more severe crisis. Our most fundamental model of the universe's structure would be off by an unknown and possibly enormous factor. Every calculation about dark matter halos, galactic evolution, and the history of cosmic assembly would need to be re-examined under the chilling assumption that for every galaxy we see, there might be 10 or 100 that we do not. Andromeda 19 is a silent warning. It tells us that the darkness between the stars is not empty but crowded with phantoms, and our ignorance of their numbers may be the greatest shadow of all. The fear of unseen multitudes leads us to a phantom discovered not by its faint starlight, but by the ghostly whisper of its raw material. Deep within the Virgo cluster, a dense gathering of galaxies over 50 million light-years away, radio telescopes picked up a strange and solitary signal. It was a cloud of neutral hydrogen gas, the fundamental fuel for star formation, radiating its characteristic radio hum. This object was catalogued as Virgo HI 21. What made it extraordinary was not its presence, but its profound isolation. This vast reservoir of hydrogen, enough to build millions of stars, was utterly alone. No galaxy, no cluster of stars, no visible structure of any kind was associated with it in optical surveys. It appeared as a dark galaxy candidate in its purest form, a swirling mass of star-making potential that had, for unknown reasons, never ignited. The discovery sent a thrill through the astronomy community. Here was the potential smoking gun for a true dark galaxy, a structure of dark matter that had gathered primordial gas but failed utterly to turn it into suns. It was a cosmic stillbirth captured in the act, a pristine example of a process that had stalled at the very first step. The implications were staggering. If confirmed, it would prove that dark matter halos could indeed exist independently, gathering normal matter but lacking the trigger, or perhaps suffering the conditions to spark the fires of creation. But monumental discoveries in cosmology are almost always met with intense scrutiny, and Virgo HI 21 was no exception. An alternative, more conventional explanation soon emerged. The cloud lies near two interacting galaxies, NGC 4254 and NGC 4255, which are slowly dancing around each other. Critics of the dark galaxy hypothesis propose that Virgo HI 21 was not a primordial object at all, but a tidal tail. This is a long, ribbon-like structure of gas and stars pulled out from a galaxy during a close gravitational encounter. In this scenario, the hydrogen cloud was simply debris, a cosmic filament of stripped material left hanging in intergalactic space after a galactic near collision. The debate became a technical duel over the cloud's dynamics. Proponents of the dark galaxy pointed to the cloud's rotation, its coherent structure that suggested it was gravitationally bound, holding itself together like a true galaxy would. Opponents argued that the rotation measurements were ambiguous and that the cloud's location and velocity perfectly aligned with what you would expect from tidal debris from the nearby galactic pair. For years, the object existed in a state of quantum uncertainty, both a revolutionary discovery and a potential cosmic mirage. The reason this confirmation is so sought after and so unsettling lies in what it would represent. A true gas-rich dark galaxy would be a unique relic. It would be a frozen moment in time, a snapshot of a universe where dark matter halos could exist in a state of permanent potential. It would tell us that the transition from dark matter clump to luminous galaxy is not automatic, that there are specific, delicate conditions required to cross that threshold. Finding one would mean that our cosmic neighborhood, filled with shining spirals and ellipticals, is just the successful fraction of a much larger, darker population of failed structures. The unsettling part is the scale of that failure. If objects like Virgo HI 21 are real and common, then the universe is far less efficient at building the stars and galaxies we see than we ever imagined. It would mean that a vast amount of ordinary matter, the very atoms that make up planets and people, is locked away in these dark, sterile reservoirs, forever out of reach of the processes that lead to life. We would have to confront a cosmos where the bright islands of light are not just rare, but surrounded by a sea of unfulfilled potential. The story of Virgo HI 21 remains unresolved, a tantalizing signature on a radio chart that holds the power to rewrite a chapter of cosmic history or to remind us that sometimes even the most promising shadows are just cast by familiar objects in an unfamiliar light. The haunting possibility of dark, gas-rich structures finds a far more personal and immediate expression closer to home. A colossal phantom is on a collision course with our galaxy, and we have named it Smith's Cloud. Discovered in the 1960s by astronomy student Gail Smith using radio telescopes, this object is a high-velocity cloud, an immense river of gas streaking through the halo of the Milky Way at over 200 miles per second. But its simple classification belies its terrifying scale and mystery. Smith's Cloud is staggering in size. It stretches over 11,000 light-years long and 2,500 light-years wide. If it were visible to the naked eye, it would span an area of the sky 30 times wider than the full moon. Its composition is almost entirely primordial hydrogen, the raw, unprocessed fuel of the universe, carrying enough gas to form over 2 million stars like our Sun. This is not a wisp, it is a continent of potential barreling through space. Its trajectory is what turns curiosity into genuine concern. Smith's Cloud is not merely drifting nearby, it is on a return path, arcing back toward the disk of our Milky Way. In approximately 30 million years, it is predicted to slam into the spiral arm we call the Perseus Arm, a region already rich with gas and dust. The impact will be a cosmic cataclysm. The shockwave from the collision will compress vast swaths of interstellar gas, triggering a fireworks display of star formation on a scale not seen in our galaxy for billions of years. It will light up a portion of the Milky Way with brilliant blue-white stellar nurseries. Yet this spectacular rebirth comes with a profound fear. The violence of such an event could be disruptive on a galactic scale, potentially sending shockwaves through the spiral structure and disturbing the orbits of countless stars, including possibly our own solar system. The deeper fear, however, lies in the cloud's origin. What is Smith's Cloud truly? Its high velocity and coherent structure suggest it is not just a random puff of gas. Many astronomers believe it is the tattered remnant of a dark galaxy, a failed structure that was torn apart by a past encounter with the Milky Way. In this scenario, it is the luminous debris, the scattered guts, of a phantom that our galaxy consumed long ago. Its current orbit is the echo of that ancient violence. Others propose it is a fragment pulled from the Magellanic Clouds, our galaxy's largest satellites during a close past. But the most unsettling possibility is that Smith's Cloud is not debris at all, but an intact, albeit gas-only, dark galaxy in its own right. A dark matter halo could be holding this vast, starless river together, guiding it on its fatal plunge. This would make it a pristine example of a dark galaxy candidate, a structure that gathered its hydrogen but never sparked a single sun, now destined to deliver its bounty to our own galactic furnace. Smith's Cloud forces us to look up and recognize a simple, chilling fact. The cosmos is not a static painting. It is a violent, dynamic arena where phantoms from the dark collide with the world of light, and one of those phantoms is already in the door, its impact inevitable. The silent approach of Smith's Cloud reminds us that collisions with the unseen are not just future possibilities, but past realities written in the twisted shapes of the galaxies we admire. Look at the beautiful spiral galaxy M99, also known as NGC 4254, in the constellation Coma Berenices. Through a telescope, it presents a classic pinwheel form, but with a glaring, unsettling asymmetry. One of its spiral arms is dramatically stretched and distorted, pulled outward as if by some immense, invisible hand. This is not a gentle imperfection, it is the signature of a violent encounter. For decades, astronomers assumed the culprit was a nearby visible galaxy, perhaps one that had brushed past it millions of years ago. But a careful census of the neighborhood revealed a problem. There is no suitable candidate galaxy close enough or massive enough to have caused such a profound distortion. The visible universe offered no explanation for the wound etched into M99's side. This absence gave birth to a haunting hypothesis. What if the damage was done by something we cannot see? The leading theory now is that M99 was struck by a dark galaxy. A massive halo of dark matter, possibly holding only trace amounts of gas and a few stray stars, plowed through the disk of the spiral galaxy. Because dark matter interacts only through gravity, the collision would have been ghostly and silent. No brilliant fireworks of colliding gas clouds, no bursts of new stars from the shock. Instead, the invisible mass would have passed through the visible disk like a cannonball through fog, its immense gravity tugging and shearing the stars and gas in its wake, leaving behind that single, grotesquely elongated arm as the only testimony to the violence. This idea is both elegant and terrifying. It provides a clean explanation for the observed damage without requiring a visible perpetrator, but it implies something far more disturbing about the cosmos. If a single, random dark galaxy can cause such havoc, then the history of every spiral we see may be filled with similar ghostly impacts. The majestic, symmetrical shapes we celebrate in astronomy textbooks may be the exception, not the rule. They might simply be the galaxies that have, so far, avoided a direct hit from the dark structures swarming around them. The fear this generates is profound. It means the stability of a galaxy, the very architecture that allows solar systems to form and persist over billions of years, is perpetually at risk from invisible, unpredictable threats. We calibrate our models of galactic evolution on visible interactions, on the slow, stately dance of galaxies we can see. But if the dark universe is constantly intruding, then our models are missing a fundamental and potentially violent piece of the puzzle. The distorted arm of M99 is more than a curiosity. It is a warning from the depths of space. It tells us that the greatest dangers may not be the brilliant, exploding stars or the gaping black holes, but the silent, massive phantoms that move through the night, reshaping reality with a gravity we can feel but never see. The scars of past collisions set the stage for a different kind of mystery, one where life emerges from the darkness against all odds. In the dense urban sprawl of the Coma cluster, a ghost is giving birth. Known as Coma P, this ultra-diffuse dwarf galaxy is a paradox in motion. Like Dragonfly 44, it is a wispy, transparent smudge, a collection of stars so spread out the galaxy is almost see-through. Its gravitational anchor is without question a massive halo of dark matter. But unlike the silent, stillborn ghosts we have encountered, Coma P is alive with activity. Deep within its faint glow, astronomers have detected the unmistakable signature of young, blue stars and the glowing clouds of hydrogen that are the cradles of stellar birth. This discovery is profoundly confusing. Our standard model of star formation is straightforward. You need a dense, cold cloud of gas. That cloud must collapse under its own gravity, a process often triggered by an external shockwave, like the blast from a nearby supernova or the gravitational squeeze of a passing galaxy. Coma P presents a problem for every part of that recipe. Its environment is the opposite of dense. Its gas is spread incredibly thin, like a fog so wispy you could barely feel it on your skin. The internal pressure within such a diffuse cloud is far too low to overcome its own tendency to just drift apart. Furthermore, in a galaxy with so few stars, supernovae are incredibly rare events, providing no regular source of triggering shockwaves. And as a small, dark matter-dominated dwarf, it lacks the strong internal gravitational tides that larger galaxies use to stir their gas. So how, in this quiet, dark, and low-density ghost town, is star formation even possible? The answer may lie in its precarious location. Coma P is not floating in serene isolation. It is adrift in the Coma cluster, a tumultuous sea of galaxies where hot gas fills the space between them. One leading theory suggests that Coma P is experiencing a form of cosmological ram pressure. As it moves through the cluster, the thin intergalactic medium acts like a gentle but persistent headwind, pressing against the galaxy's own sparse gas. This subtle, galaxy-wide compression might be just enough to nudge some gas clouds over the critical edge, initiating a slow, fragile cascade of collapse. It is star formation on life support, a faint sputter of creation fueled by the galaxy's motion through a hostile environment. This turns our understanding on its head. We have always thought of dense, turbulent nurseries like the Orion Nebula as the ideal factories for stars. Coma P suggests that in the darkest, quietest corners of the universe, the barest whisper of external pressure can be enough. It forces astronomers to ask a humbling question: have we been too narrow in defining the conditions for life? If stars can be born in the ghostliest of galaxies, then the potential for planetary systems, and perhaps even life itself, may extend far beyond the bright spiral arms we call home, into the vast and shadowy frontiers of the cosmos. This fragile starlight in the darkest corners is not an isolated phenomenon. Among the first to reveal this hidden population was a ghost in the group of galaxies surrounding NGC 5846. Catalogued simply as NGC 5846 UDG1, this object was a landmark discovery. It was one of the very first ultra-diffuse galaxies ever identified not in a dense, violent cluster, but in a quieter group setting, a small galactic neighborhood. Its appearance was deceptively simple, a large, smooth, and faint smudge of ancient stars, but its properties were anything but ordinary. For its incredibly low surface brightness, this galaxy was enormous, stretching tens of thousands of light-years across, a size comparable to our own Milky Way. Yet it contained less than 1% of our galaxy's stars. It was a cosmic feather, vast in expanse but almost weightless in light. The true shock came when astronomers studied its system of globular clusters. These are dense, spherical swarms of hundreds of thousands of ancient stars that orbit a galaxy like bees around a hive. Large, massive galaxies tend to have many globular clusters, while small, faint ones have few. NGC 5846 UDG1 defied this logic completely. This faint, wispy phantom possessed a rich system of globular clusters, far more than any galaxy of its dim luminosity should have. The implications were immediate and profound. Globular clusters are tracers of gravitational might. Their number and distribution reveal the mass of the invisible halo holding them. For this ultra-diffuse galaxy to host so many, it had to be embedded in a dark matter halo of staggering proportions, a halo as massive as that of the Milky Way itself. Here was the chilling formula again, a ghostly, transparent galaxy with the gravitational footprint of a giant. This discovery shifted the entire conversation. Before UDG1, ultra-diffuse galaxies were curiosities, perhaps odd products of the brutal cluster environment. Finding one in a Coma group proved they could form in more ordinary places. And its massive dark matter halo suggested these were not failed, insignificant fragments, but failed giants. They had gathered the dark matter skeleton of a major galaxy, but for reasons unknown, failed to dress it in a full suit of stars. This realization sparked a specific and growing fear among cosmologists. If objects like NGC 5846 UDG1 exist in relatively nearby groups where our telescopes are most powerful, then they are likely everywhere. They are not rare mistakes, but a common, perhaps even dominant, population of galaxies we have been blind to for centuries. Every faint smudge we dismissed as a flaw in the lens, every empty patch of sky, might be hiding one of these dark titans. UDG-1 was not just a discovery, it was a warning. It forced astronomers to confront the terrifying possibility that the glittering spiral and elliptical galaxies we have catalogued for generations are merely the tip of the cosmic iceberg. Below the surface of visibility, in the cold, dark sea of intergalactic space, there could be a submerged continent of dark matter structures, outnumbering the luminous galaxies we hold dear. The discovery of individual phantoms like UDG-1 was just the beginning. To truly understand the scale of this hidden population, astronomers needed to cast a wider net, one that could sweep across vast stretches of the cosmos. That net was the Arecibo Legacy Fast Alpha Survey, known simply as Alfalfa. For years, the Great Arecibo Radio Telescope in Puerto Rico, before its tragic collapse, performed a monumental task. It systematically scanned the sky not for starlight, but for the faint radio whisper of neutral hydrogen gas. This primordial fuel emits a specific frequency when its electron spins flip, a signature as reliable as a fingerprint. Alfalfa was not looking for bright galaxies, it was listening for the raw material of creation itself, and what it heard was a chorus of mysteries. The survey catalogued thousands of hydrogen clouds, many associated with known galaxies. But a troubling subset stood apart. These were isolated clouds of hydrogen, spinning with the coherent motion of a structured object, yet with no visible stars to account for that motion in optical follow-up observations. They were dark galaxy candidates by the dozens. The methodology seems straightforward in principle. Find a cloud of hydrogen rotating too quickly to be held together by its own gas. Calculate the mass required to keep it from flying apart, and then compare that to the minuscule amount of light coming from the same spot. If the mass is hundreds of times greater than the light can explain, you have a strong candidate, but confirmation is a nightmare of cosmic proportions. The first and greatest challenge is distance. Measuring how far away one of these faint radio whispers truly is incredibly difficult. A misjudgment of even a small percentage can turn a massive, distant dark galaxy into a much smaller, closer, and more mundane puff of gas. The second challenge is the ever-present ghost of tidal debris. As we saw with Virgo HI-21, long streams of gas ripped from galaxies during collisions can masquerade as coherent, rotating objects, especially when viewed from a specific angle. Proving a cloud is truly primordial and isolated, and not just the scattered entrails of a past galactic encounter, requires exquisitely detailed maps of its surroundings and motion, a painstaking process for each and every candidate. Yet, despite these hurdles, the Alfalfa survey left an indelible mark. It provided statistical weight to a growing fear. The sheer number of strong candidates it identified suggests these objects are not rare anomalies. They could be a fundamental component of the cosmic landscape. The fear is that the universe is teeming with these dark, primordial objects, vast reservoirs of hydrogen locked in the grip of dark matter, forever waiting for a spark that never comes. If even a fraction of the Alfalfa candidates are confirmed, it would mean that a significant portion of the universe's ordinary matter exists in this dark, sterile state. It paints a picture of a cosmos where the process of galaxy formation is inefficient on a staggering scale, where dark matter gathers the ingredients for light and life, but more often than not, the recipe fails. We are left listening to the echoes of that failure, the silent spin of hydrogen clouds in the void, each one a question mark written in the oldest language of the universe. The silent hydrogen clouds catalogued by Alfalfa find a dramatic and violent counterpart in a spectacular cosmic wreck. Near the southern constellation Centaurus, a chaotic system unfolds around a peculiar galaxy named NGC 5291. This is not a serene spiral, but a collisional ring galaxy, a glowing loop of intense star formation created by a direct hit. Billions of years ago, another galaxy plunged straight through the heart of NGC 5291, sending shockwaves rippling outward that compressed gas into a brilliant ring of newborn stars. The violence of that ancient collision did more than reshape one galaxy. It seeded the surrounding space with debris on a monumental scale. Orbiting this luminous wreck are several enormous clouds of hydrogen, each one a potential island of matter cast adrift. Among these orphans, one stands out so dramatically that astronomers have, with cautious boldness, nicknamed it simply the Dark Galaxy. This object is a behemoth of pure potential. Observations show it contains a staggering amount of neutral hydrogen gas, nearly 1 billion times the mass of our Sun. That is enough raw material to build an entire dwarf galaxy's worth of stars. Even more telling, this vast cloud is not static, it is spinning. Its coherent rotation reveals it is held together by its own gravity, behaving as a distinct, structured entity rather than a formless puff of debris. When scientists calculated the mass needed to keep this swiftly spinning cloud from flying apart, they arrived at a number far greater than the mass of the hydrogen alone. The conclusion points to a massive, unseen anchor, a halo of dark matter providing the gravitational glue. Here, then, appears to be a dark galaxy in near-perfect form, a frozen recipe. It possesses the dark matter skeleton. It has gathered the gaseous ingredients, but the final step, the ignition of star formation, has not occurred. It represents a cosmic pause button, a snapshot of a galaxy caught in a moment of permanent potential. The debate now centers on why it remains frozen and whether that pause is temporary or eternal. The environment holds a clue and a contradiction. The cloud orbits within a system still reverberating from a colossal collision, awash in shockwaves and turbulent energy. Such an environment should, in theory, be the perfect trigger to compress gas and spark star birth. Yet the dark galaxy near NGC 5291 remains dark, its hydrogen cold and quiet. One possibility is that the cloud is simply too diffuse, its internal pressure too low to initiate collapse even with external jostling. Another, more profound idea is that it lacks the necessary seeds, the tiny dust grains that act as catalysts for gas to cool and clump. Without this cosmic grit, the gas may remain too hot and energetic to condense, forever suspended on the brink. This leads to the unsettling question: is this object a galaxy that will be, or a galaxy that never can be? If it is forever stalled, it becomes a museum piece of a specific evolutionary stage, a testament to the delicate and poorly understood conditions required to turn darkness into light. Its very existence suggests that the universe is filled with such aborted beginnings, structures that gathered everything they needed except the final, elusive spark. Studying this dark cloud is like watching a paused film of galactic birth, a film we are not sure will ever start playing again. The Dragonfly family of cosmic phantoms extends far beyond its famous first member. Another ghost, catalogued as Dragonfly 17, drifts through the same dense coma cluster as its sibling, and its story reinforces a terrifying pattern. Like Dragonfly 44, this galaxy is an ultra-diffuse spectre, a vast, wispy smudge of ancient stars that appears almost transparent against the blackness of space. Its physical size is comparable to our own Milky Way, yet its light output is pitifully faint, a mere whisper of starlight spread across an immense volume. The measurements tell the same unsettling tale. The motions of its sparse stars betray the presence of a massive, anchoring dark matter halo, a gravitational titan cloaked in near-total darkness. Dragonfly 17 is not an oddity, it is a confirmation. It proves that Dragonfly 44 was not a solitary freak of nature, but a representative of an entire population hiding in plain sight. The existence of multiple such phantoms within a single cluster forces a chilling re-evaluation of what we thought we knew about cosmic environments. Galaxy clusters like Coma were long considered stellar metropolises, places where the density and violence should produce bright, classic elliptical galaxies or completely shred fragile dwarfs. The prevalence of large, faint galaxies like the Dragonflies turns that assumption on its head. Instead of being destroyed, these ghosts are not just surviving in the cluster, they may be a direct product of it. This suggests a paradigm shift so profound it borders on scary. Perhaps the brutal environment of a cluster does not always lead to brilliant star-filled giants. Instead, the very processes we thought built galaxies, the ram pressure of intergalactic gas and the relentless gravitational tides, might in some cases have the opposite effect. They could be stripping away star-forming gas efficiently and early, leaving behind only the dark matter skeleton and a tenuous shroud of old stars, creating these ultra-diffuse phantoms as a final frozen state. If true, then the shining galaxies we see are not the default outcome of cosmic evolution. They might be the lucky ones that formed in quieter neighborhoods away from the violent crowds. The Dragonfly family, growing with each new discovery, forces us to confront a universe where the most common galactic form in dense regions might not be a brilliant spiral or a glowing elliptical, but a vast, dark, and silent shadow. But the Dragonfly family's immense halos are not the only way darkness can concentrate. Sometimes the most extreme densities are found in the smallest, most unassuming packages. Take Segue II, a name that sounds like a minor footnote but belongs to one of the most puzzling objects in the Milky Way's halo. This is not a large, wispy phantom, but a tiny, compact dwarf galaxy, a mere smattering of ancient stars. Its visible population is almost laughably small, containing only a few hundred stars in total, a stellar gathering so meager it barely qualifies as a cluster, let alone a galaxy. If our sun were a resident of Segue II, the night sky would be a profound and lonely blackness, with only a handful of faint, red points of light to break the endless dark. Yet this pathetic glow tells a monstrous lie. When astronomers measured the motions of those few stars, they found them zipping around at velocities that should have sent them flying off into space long ago. The only thing holding this tiny knot together is gravity from an unseen source of staggering density. The math reveals a terrifying imbalance. For its minuscule stellar mass, Segue II must be embedded in a dark matter halo that is thousands of times more massive. The core of this halo is so incredibly dense and compact that it defies easy explanation. This turns a fundamental expectation on its head. We used to think the largest galaxies with their vast gravitational wells were the ultimate dark matter traps. Segue II suggests the opposite might be true. The smallest, faintest dwarf galaxies could be the most efficient dark matter concentrators in the universe. This realization sparks a specific and profound fear among particle physicists. Dark matter is not a uniform fluid. It is theorized to be made of individual particles. In these ultra-dense cores, the particles will be packed together unimaginably tightly. If dark matter particles can interact with each other, even weakly, the rate of collisions and annihilations in a place like Segue II would be astronomical. It should be a blazing beacon of gamma rays, the energy signature of dark matter destroying itself. Our most sensitive telescopes have stared at Segue II and they see almost nothing. The expected gamma ray glow is missing. This silence is louder than any explosion. It means one of two terrifying things. Either our models of the dark matter halo's density are wildly wrong, and Segue II is not as dense as we think, which would undermine our gravitational measurements. Or, and this is the more unsettling possibility, dark matter particles simply do not interact with each other in the way our leading theories predict. They might be even more dark than we imagined, incapable of annihilating at all. This would force us to abandon some of our most promising ideas for detecting it. Segue 2, this tiny speck of light, becomes a cosmic laboratory testing the very nature of the universe's dominant substance. Its profound darkness is not just an absence of stars, but a silence that speaks volumes, telling us that the rules of the shadow universe may be stranger and more elusive than we ever dared to fear. The profound silence of Segue 2 echoes a far larger and more systemic fear that has haunted cosmology for decades. We call it the missing satellites problem, and it strikes at the very heart of our understanding of the universe's structure. Our most sophisticated computer simulations of cosmic evolution, based on the prevailing lambda cold dark matter model, paint a very specific picture of our galactic neighborhood. They show that as a giant spiral like the Milky Way forms, it should be surrounded by a vast swarm of smaller dark matter clumps, the leftover building blocks from its assembly. The numbers from these simulations are staggering, predicting thousands of these substructures orbiting our galaxy. Yet, when we look up with our most powerful telescopes, we only see a few dozen visible dwarf satellite galaxies. For years, this was a glaring contradiction, a hole in our theory so large you could fly a galaxy through it. Where were all the missing satellites, the discovery of ultra-faint dwarfs like Segue 1 and Segue 2, galaxies so dim they were once invisible to us, helped close the gap? We realized our census was incomplete, that we were only seeing the brightest tip of the galactic iceberg. But a more terrifying solution has emerged, one that transforms the problem from a puzzle into a profound existential question. What if the majority of those predicted dark matter clumps never manage to form stars at all? What if they are not missing, but right here, completely dark? This is the ultimate cosmological fear. Our neighborhood, which we perceive as a relatively orderly system with a bright central spiral and a few dozen faint companions, could in reality be a teeming metropolis of invisible structures. Every prediction of those thousands of dark matter halos could be correct. They could be orbiting us right now, vast gravitational islands of pure shadow, utterly devoid of the starlight that would give them away. The implications of this are chilling on multiple levels. First, it means the Milky Way's gravitational landscape is far more complex and crowded than our maps suggest. The gentle gravitational tugs and tidal forces that shape the orbits of stars and gas clouds within our galaxy are not just coming from the few satellites we see, but from a hidden multitude. This invisible architecture could explain subtle anomalies in the motions of outer stars or the structure of our galactic halo that have long puzzled astronomers. Second, and more fundamentally, it suggests that the process of galaxy formation is astonishingly inefficient. The universe seems to have no trouble making the dark matter scaffolding, but turning that scaffolding into a luminous galaxy appears to require a very specific and delicate set of conditions, a cosmic alignment that fails far more often than it succeeds. If most dark matter halos remain dark, then the bright galaxies we cherish and call home are the rare exceptions in a cosmos dominated by silent, sterile shadows. This transforms our place in the universe from a typical resident of a shining city to a fortunate inhabitant of a lone lighthouse in a vast, dark ocean. The fear is not that the satellites are missing, but that we are surrounded by ghosts, and we have only just begun to sense their silent, gravitational presence. This invisible architecture of our present universe finds its origins in the deepest past, in an era when the cosmos was a featureless sea of darkness. After the Big Bang, the universe cooled into a neutral fog of hydrogen gas, a state known as the cosmic dark ages. Then something happened to lift that fog. Something produced enough high-energy ultraviolet photons to rip electrons from those hydrogen atoms, reionizing the universe and making it transparent to light for the first time. We know this reionization epoch occurred, but the identity of the cosmic heroes who did the heavy lifting remains one of cosmology's greatest mysteries. The leading suspects have always been the first brilliant galaxies and quasars, whose fierce radiation could have carved transparent bubbles in the primordial haze. But there is a persistent, nagging problem with this story. When we count up the known early galaxies and quasars from that time, their combined output falls short. There simply do not seem to be enough of these bright beacons to have reionized the entire universe so quickly. This glaring deficit points to a missing population, a hidden workforce of ultraviolet producers. And here is where a terrifyingly elegant possibility emerges. What if the primary engines of reionization were not the brilliant galaxies we can see, but the dark ones we cannot? Imagine a universe filled with countless small, gas-rich dark matter halos. These are the pristine dark galaxies, structures that gathered hydrogen fuel, but because of their low mass or quiet environments, formed stars only sporadically and inefficiently. They would not be dazzling spirals, but faint, flickering smudges. Crucially, even a low level of star formation produces high-energy ultraviolet radiation. In a single, massive galaxy, that radiation might be trapped by its own dense gas. But in a vast population of small, diffuse, dark galaxies, the radiation could easily escape into intergalactic space. It is a numbers game with profound stakes. A trillion faint, dark galaxies, each leaking a tiny trickle of ultraviolet photons, could collectively flood the cosmos with more ionizing radiation than a smaller number of brilliant giants. This theory solves the energy deficit elegantly, but it introduces a paralyzing fear for cosmologists. It means the key actors in one of the most important transformations in cosmic history, the event that cleared the stage for all future galaxy formation, might be almost entirely invisible to our most powerful telescopes. We are trying to reconstruct the plot of the universe's origin story by only studying the supporting characters, while the protagonists remain hidden in the shadows. Every observation we make of the early universe, every distant galaxy we painstakingly catalogue with the James Webb Space Telescope, could be just a minor player in a drama dominated by ghosts. If dark galaxies were the primary architects of reionization, then our entire narrative of cosmic dawn is built on a foundation we cannot see, a history written in light that has long since faded, leaving behind only the echo of its effect on the ancient hydrogen fog. The fear is that we may never fully witness the event that made the universe transparent, because the tools that did the work were made of darkness. The profound possibility of a dark cosmic dawn leads us to a ghost so faint it seems to dissolve before our eyes. In the constellation of sextants, a team from the Instituto de Astrofísica de Canarias, the ISC, recently found something that should not be possible to see. They named it Nube, the Spanish word for cloud, and it is a perfect, terrifying name. This dwarf galaxy is a record breaker, the faintest galaxy of its size ever detected in the nearby universe. Its surface brightness is so incredibly low that it is 50% dimmer than any previously known object of its kind, a smudge of starlight so subtle it pushes our most advanced telescopes to their absolute limits. Nube is not just a faint patch, it is a whisper at the edge of silence. Its structure deepens the mystery. Unlike the spherical puff of Crater 2, Nube is elongated, stretched into a delicate filament of ancient stars. This shape is not easily explained by the gentle tides of a parent galaxy, suggesting it may have formed this way, a primordial wisp from the beginning of time. The sheer faintness of Nube is what instills a specific, chilling fear in astronomers. Finding it required a specialized technique, stacking and processing ultra-deep images to tease its signal from the random noise of the night sky itself. This is not standard observational astronomy, it is forensic archaeology of the void, and that is the terrifying implication. If an object this dim, this large, and this close by has only just been discovered, what does it say about our map of the cosmos? Nube is not an anomaly, it is a benchmark. It defines a new threshold of darkness, a line below which an entire universe of structure may be hiding. every empty patch of sky in every galaxy group we study could be concealing similar phantoms, a submerged continent of ultra-diffuse shadows that our current surveys are completely blind to. Nube is a warning written in the faintest possible ink. It tells us that the hidden population we fear is not just numerous, but likely far more ghostly than our most pessimistic estimates. The faintest whispers often reveal the most terrifying truths, and the ancient dwarf galaxy Tucana II is a testament to that. Orbiting the Milky Way at the distant fringe of our galactic halo, Tucana II is an ultra-faint fossil, a collection of stars so old and metal-poor they are relics from the universe's first billion years. For a long time, astronomers believed this galactic speck was exactly what it appeared to be, a tiny, isolated cluster of primordial stars, perhaps one of the original building blocks of our galaxy. But then, a team using data from the Gaia spacecraft made a startling observation. They found several stars moving through space at the same velocity and direction as Tucana II, but located astonishingly far from its main body, up to several thousand light-years away. These were not random field stars, they were members of the same family, gravitationally bound to the dwarf galaxy despite being flung far into the void. This discovery was like finding a planet's atmosphere extending 10 times farther than the planet itself. It meant the gravitational influence of Tucana II, the reach of its invisible mass, was vastly larger than its visible starlight suggested. The only force capable of holding these distant stars in such a tenuous grip is dark matter. Tucana II is not just embedded in a dark matter halo, it is the tiny, luminous tip of a monstrous iceberg of shadow. The halo extends over 5 times farther than the span of its visible stars, a hidden sphere of gravitational dominance that makes the true Tucana II a colossus. This hidden size is what sends a chill through the scientific community. If we had looked only at the starlight, we would have catalogued Tucana II as a minor, insignificant satellite. But its dark matter halo tells a different story, one of immense, unseen power. The fear this generates is not about a single galaxy, but about our fundamental method of observation. Tucana II suggests we are consistently, perhaps catastrophically, underestimating the true physical scale of dark matter structures throughout the cosmos. Every faint dwarf galaxy we map by its stars could be the glowing nucleus of a dark matter sphere that engulfs it, a hidden gravitational territory orders of magnitude larger. This transforms our mental map of the Milky Way's neighborhood from a sparsely populated frontier with a few dozen visible satellites into a densely packed realm where vast spheres of dark matter overlap and interact, their true boundaries completely invisible to us. The distant stars of Tucana II are like buoys marking the edge of a dark ocean, and the ocean is far wider and deeper than we ever dared to believe. The hidden ocean of dark matter surrounding Tucana II forces us to question the very identity of every faint smudge we find. This crisis of classification becomes terrifyingly personal with an object known as Willman I. Discovered in 2004 by astronomer Beth Willman, this tiny collection of stars sits in the constellation Ursa Major, a mere 120,000 light-years from Earth. From the moment of its discovery, Willman I refused to fit neatly into any cosmic category. It contains only a few hundred ancient stars, a number so small it blurs the line between two fundamentally different kinds of objects. On one hand, it could be an ultra-faint dwarf galaxy, the smallest and darkest type of galaxy, held together by its own massive dark matter halo. On the other, it could be a globular cluster, a dense, spherical swarm of stars that form together and orbits the Milky Way, bound only by the gravity of its visible stars with little to no dark matter. The problem is, Willman I exhibits unsettling characteristics of both, and the distinction is not academic. It is a fork in the road that leads to two completely different and equally frightening interpretations of reality. If Willman I is a galaxy, then its properties are deeply anomalous. its handful of stars are moving with a velocity dispersion, a measure of their random motions that is surprisingly high. To keep these swiftly moving stars from flying apart, the object must possess a significant amount of dark matter, perhaps over 99% of its total mass. This would make it an extreme example of a dark matter-dominated fossil, a galaxy where the ratio of shadow to light is almost comically skewed, but this conclusion creates its own puzzle. Why is a galaxy so efficient at gathering dark matter so utterly incompetent at forming stars? Its stellar population is pathetically small, even for an ultra-faint dwarf. It suggests a formation process that went horribly wrong, or was violently interrupted almost immediately after it began. The fear here is that we do not understand the minimum threshold for galaxyhood. How little starlight can a true dark matter halo produce and still be called a galaxy? Willman 1 seems to test that limit, but if Willman 1 is a globular cluster, the fear simply shifts to a different domain. Classic globular clusters are brilliant, dense spheres of up to 1 million stars, and their internal dynamics are governed purely by the gravitational pull of those stars. They do not require and are not expected to have significant dark matter halos. Yet, the measured motions of stars in Willman 1 are too fast to be explained by the gravity of its visible stars alone. If it is a cluster, then our understanding of how star clusters work is fundamentally flawed. Perhaps it is the remnant core of a much larger dwarf galaxy that was almost completely stripped away, leaving behind this dense nugget of stars still embedded in a tiny whisper of its original dark matter halo. Or maybe some globular clusters can form with or later acquire dark matter, a possibility that would rewrite textbooks on stellar archaeology. This ambiguity is the true source of dread. Willman 1 is a cosmic Rorschach test, and what we see in its faint blur tells us more about our own ignorance than about the object itself. Its unresolved identity highlights a terrifying truth. At the frontier of detection, where our instruments strain to see the faintest whispers of light, the universe's categories break down. The clear lines we draw between galaxy and cluster, between dark matter structure and pure stellar aggregate, may be illusions of our limited perspective. Willman 1 forces us to admit that we might be looking at an entirely new class of object, one for which we have no name and no theory, a silent hybrid born from shadows we are only beginning to perceive. The unresolved identity of objects like Willman 1 points to a deeper, more pervasive haunting woven into the very fabric of our galaxy. Look up at the Milky Way's band of light, and you're not seeing a pristine, isolated spiral. You are witnessing an ancient crime scene, the aftermath of a continuous feast. Our galaxy grew by consuming others. The evidence is written in rivers of stars that flow through the galactic halo, ghostly streams that trace the final orbits of devoured dwarf galaxies. The most famous of these is the Gaia sausage, or Enceladus, the remains of a massive dwarf galaxy that collided with the young Milky Way over 10 billion years ago. Its stars were torn apart and smeared into a vast hot cloud that now forms the inner halo, fundamentally shaping our galaxy's structure. We see similar, thinner streams like the Sagittarius stream still wrapping around the Milky Way in delicate stellar ribbons. These are the luminous graves of galaxies that no longer exist, but here lies a profound and unsettling question. When the Milky Way tore apart a dwarf galaxy, what happened to its dark matter? The stars and gas, the visible components, were shredded into streams we can now map, but dark matter, which does not collide or clump like normal matter, would have behaved very differently. As the dwarf galaxy was ripped apart, its massive dark matter halo would not have been destroyed. Instead, it would have simply passed through the collision, becoming unbound and dispersing. This means the ghostly remains of those ancient halos are likely still here. They are disembodied, invisible phantoms haunting the Milky Way's vast halo, massive clouds of pure shadow that no longer have any stars to call their own. They are the echoes of galaxies that died long ago, but their gravitational influence never left. This realization transforms our understanding of the galactic environment. The Milky Way's halo is not a smooth, spherical cloud of dark matter. It is likely lumpy and chaotic, filled with these lingering dark matter subhalos, the skeletons of past meals. They are undetectable by any direct means, yet their gravity subtly tugs on everything. They could distort the paths of distant stars we track, create unexpected ripples in the outer gas disk, and influence the very motion of the solar system as it orbits the galactic center. We calibrate our models of the galaxy's mass and rotation based on the gravity we can measure from visible stars and gas. But if a significant portion of that gravitational field comes from these invisible, chaotic ghosts, our models are built on a foundation we cannot see. The fear is that we are trying to map the shape of a haunted house by only studying the furniture, completely unaware of the unseen presences in every room, whose silent footsteps shift the floorboards and bend the light. Every stellar stream we discover is not just a relic of a past galaxy. It is a tombstone marking where a dark matter phantom was set free. These lingering dark matter phantoms, silent and unseen, may have just given us a way to scream. Across the cosmos, brilliant and baffling flashes of radio energy erupt without warning, phenomena known as fast radio bursts. Lasting mere milliseconds, each burst releases more energy than our sun emits in 80 years. Many of these bursts are repeaters, flashing from the same spot in the sky over and over, often traced back to the chaotic neighborhoods of neutron stars within active galaxies. But a more frightening category exists, the one-off bursts. These are singular, catastrophic explosions that happen once and are never heard from again. They flash into existence from random points in the sky and vanish just as quickly, leaving behind no trace, no repeating signal, and no obvious source. Their origin is one of the greatest puzzles in modern astronomy. Where do these titanic, solitary flashes come from? One speculative and deeply unsettling theory points directly to the realm of dark galaxies. Imagine a massive, pristine dark matter halo, one of those failed giants we have discussed. Within its vast, cold expanse, it holds a swirling reservoir of hydrogen gas, but no stars, no light, no obvious source of violence. Now imagine a cataclysm, perhaps a supermassive black hole formed by some unknown process in the total dark, suddenly activates and consumes a vast cloud of gas in one gulp. Or maybe an exotic object like a magnetar, a neutron star with a magnetic field a quadrillion times stronger than Earth's, forms in the darkness and suffers a catastrophic starquake, its crust shattering and releasing a tsunami of radio waves. In a normal galaxy, such an event would be accompanied by a host of other electromagnetic signatures, X-rays, gamma rays, or a visible afterglow. We could pinpoint the host galaxy with ease. But if this detonation occurs in a true dark galaxy, a structure with no stars and only trace amounts of gas, the environment would be utterly different. The brilliant radio flash would erupt from the darkness, travel across the universe, and slam into our telescopes. Yet when we point every other instrument we have at that exact spot, we would see nothing. No host galaxy, no lingering glow, just empty black space. That is the terrifying prospect. The most powerful, singular explosions in the universe might be coming from places that do not, in any conventional sense, exist. These one-off fast radio bursts could be the death cries of monsters in the dark, the only fleeting evidence of entire galaxies that live and die in total shadow. This transforms these bursts from mere cosmic curiosities into potential probes of the invisible universe. Each unexplained flash becomes a lighthouse beam sweeping from a shore we cannot see, momentarily illuminating a hidden continent of dark matter. The fear is not just about their power, but about their testimony. If even a fraction of one-off bursts are confirmed to come from empty patches of sky, it would be the strongest indirect evidence yet that the cosmos is teeming with dark galaxies. Every brilliant, mysterious flash would then be a funeral pyre for a world that never knew light. A final, spectacular confession from the dark universe that it is far more alive and far more violent than we ever dared to dream. The most terrifying possibility is not the existence of a few dark phantoms, but their absolute dominion. After encountering 24 of these shadows, from the ghostly dragonflies to the silent whispers like Nube, a final, chilling pattern emerges. What if dark galaxies are not the exception but the rule? This is the ultimate fear that concludes our journey. The luminous galaxies we cherish, the spirals and ellipticals we have catalogued for centuries, may be nothing more than rare ornaments, glittering baubles hanging on a vast, invisible framework of darkness. Our entire map of the cosmos, built from points of light, would then be a map of the exceptions, not the reality. We would be fundamentally blind to the true architecture of the universe. Consider the sheer numbers implied by our discoveries. The missing satellites problem suggests thousands of dark matter clumps surround our galaxy. Surveys like Alfalfa hint at legions of isolated hydrogen clouds. Each ultra-diffuse galaxy we find, like those in the Coma cluster, seems to have dozens of siblings too faint to see. If you add these clues together, the mathematical weight tips toward a terrifying conclusion. For every brilliant spiral like the Milky Way, there could be 10 or 100 or 1,000 dark counterparts. These are not failed galaxies in the sense of being mistakes, but successful dark matter structures that represent the most common outcome of cosmic evolution. Star formation, the process that builds everything we see and are, would be a fragile and inefficient side effect, a flicker of light in an ocean of shadow. This realization forces a profound and humbling shift in perspective. Astronomy has always been the study of light. We built telescopes to collect photons, we analyze spectra to understand chemistry, we measure brightness to gauge distance. Our entire science is built upon the assumption that what shines is what matters. But if the universe is dominated by dark galaxies, then our entire field of view is a biased sample. We are like deep-sea creatures who have only ever studied the few fish that glow, completely unaware of the massive, dark-bodied leviathans that move silently through the blackness around us. Our theories of galaxy formation, of cosmic evolution, of the universe's history, are all calibrated on this glowing minority. If the majority of structures are invisible, our foundational theories are built on a statistical error of catastrophic proportions. The terror here is not of monsters, but of ignorance on a cosmic scale. It means the true skeleton of the cosmos, the massive gravitational framework that dictates the flow of galaxies and the fate of the universe, is one we cannot perceive. The great cosmic web, with its filaments and nodes, might be primarily defined by dark galaxies, with the shining ones merely tracing the brightest intersections. The collisions that shape galactic destinies, like the one that scarred M99, might be far more common than we know, happening silently between invisible giants. Even the expansion of the universe itself, driven by dark energy, is measured through the light of supernova invisible galaxies. If those galaxies are unrepresentative outliers, our most fundamental cosmological parameters could be subtly, yet profoundly, wrong. This brings us to a final, reflective question. What does it mean for our place in the universe if we are the product of a rare and fragile process? Our solar system, our planet, and every life form upon it exists because a particular dark matter halo, against all odds, successfully ignited a prolific era of star formation. We are not inhabitants of a typical cosmic structure. We are residents of a luminous aberration, a fortunate spark in an endless night. The 25 dark galaxies we have explored are not just curiosities, they are messengers. They carry the same silent testimony, a warning that the universe we see is a carefully lit stage, and behind the curtains in the overwhelming darkness lies the true, unseen performance. Our greatest fear and our greatest challenge is to learn how to see in the dark. This journey through 25 silent phantoms has reshaped the night sky. Each one, from the massive ghost Dragonfly 44 to the faint whisper of Nube, is not merely a curiosity, it is a direct challenge. They defy our models of how galaxies are born, survive, and die. They force us to rewrite the cosmic rulebook with every new discovery. The fear they instill is not of monsters, but of the profound scale of our own ignorance. We have mapped a universe of light, only to find it floating on an ocean of shadow. These dark galaxies are the quiet revolutionaries of cosmology, proving that what we see is only a fraction of what is real. They suggest our home, the brilliant Milky Way, may be a rare and fortunate spark in a cosmos dominated by darkness. So the next time you look up at the stars, remember the phantoms. Remember that for every point of light, there may be a vast, invisible structure holding it in place, a silent giant whose gravity we feel but whose face we will never see. This is the true frontier, not the distant past, but the hidden present all around us. Which of these dark galaxies frightens you the most? Is it the approaching continent of Smith's cloud, or the silent annihilation signal from Triangulum II? Share your thoughts below, and if you crave more journeys into the cosmic unknown, subscribe now. The universe is stranger than we dreamed, and the greatest mysteries are still waiting in the dark.